Hello, Chemistry 11 Honors. This is Mr. Chan, and this is the second lesson which we talked about work and heat. Now, recall last day we talked about this idea of molar heat capacity, specific heat capacity, and then I went over some of the questions. Hopefully you had a chance to practice that. Now, if we scroll down, we continue on. What if we were to put it together? If we take all of the heat and the work entering or leaving the system, we can calculate something called delta E, or the change in energy. Now, you were exposed to that formula back in, I believe it's page 243 or 244 in your zoomed all text. Now, what we can do is if the change in energy is equal to Q, which is heat plus work, remember, Q is equal to heat and work is negative P delta V. Remember, this was from the equation up here. All right, work is equal to negative P times delta V. So we scroll back down. Rearranging it, we have Q is equal to delta E, or the change in energy, plus the pressure times the change in volume. Now, if we have a constant volume, then what happens is the change in volume is 0. So the heat of the system is equal to the total change in energy. We also have, if the pressure is constant, we have the change in energy plus the pressure times the change in volume. We have Q at a constant pressure. Now, enthalpy, H is defined as H is enthalpy is equal to the energy plus the pressure and volume, and is a state function. So delta H is equal to delta E, which is equal to delta PV, change in pressure times volume. And since pressure is constant, then we can modify the equation as delta H is equal to delta E plus P delta V. Notice the two equations are the same. So what we have is energy at a constant pressure is delta H. Now, when we talk about constant pressure, usually we're talking about atmospheric pressure because reactions occur at sea level. Now, since Q and delta H are talking about energy, both of the terms have the same units of kilojoules per mole. And for most reactions, because delta H is equal to delta E, because there's little to no change in the volume. So what happens is the change in volume is so minuscule, delta H is equal to delta E. And like change in energy, delta E, one needs to calculate the change in enthalpy of a system from the reactants to the products or vice versa. So this is why, going back to chemistry 11, when we did the chemical reactions, notice the term here is delta H, because what you're looking at is the change in energy from reactants to products, or from products to, in this case, from reactants to products. Now, delta H of a system depends on the physical states of the reactants and products, as well as the conditions of the reaction. Okay, and the enthalpy change for a reaction is equal but opposite in sign for delta H of the reverse reaction. Okay, so a couple of key things you might want to highlight is the enthalpy change for a reaction is equal but opposite in sign for delta H of the reverse reaction. Okay, and generally reactions tend to go to the side with lower enthalpy or lower energy because the bonds are more stable. This we'll talk about a little bit more in chemistry 12, but at this point in time, just be aware of those 3 bullets. Now, delta H is generally measured at a standard set of condition called thermodynamic standard state, and is represented by this delta H naught. So you will notice, oopsie. And whoopsie. Meeting, share screen. Sorry, a little bit of technical glitches there. Delta H is generally measured as standard state set of conditions called thermodynamic standard state. And what you will notice is it's represented by this little circle here. Now, when we talk about standard state, thermodynamic standard state, it represents 25 degrees Celsius or 298 Kelvin, 1 atmosphere for each gas, and 1 molarity of solutions. Okay. Now, let me give you a typical example of what I mean, of how we can do this. It says how much heat is released when 4.5 grams of CH4 is burned in a constant pressure system. Now, the delta H for the reaction is -890 kilojoules per mole reaction. Now, you recall from earlier on, the negative value means that it is exothermic. Now, notice I use the word here, mole of reaction. Now, what that means is that it could be for 1 mole of CH4 or 2 moles of O2 or 1 mole of CO2, etc., based upon the coefficients. Okay, so in this particular case, the first step is you want to find the moles of CH4. So you go back to 4.50 grams times 1 mole of CH4 all over 16.0 grams of CH4. And what that would do is it'd be 4.50 divided by 16. That would give you 0.2813 moles of CH4. Now, to calculate the grams, so step 2, I would take the 0.2813 of moles times -890 kilojoules for every 1 mole. And that gives me an answer of -250.3 kilojoules. Now, again, what does the negative mean? It just means that it is an exothermic reaction. And it corresponds to the question when it says heat is released. So that also reconfirms that it's an exothermic reaction. Now, again, if you take a look at your textbook, and if I can get that here, if you take a look on page 247, what happens is on page 247, they give you an example. It's, oh, look, it's almost the exact same question. Okay, so 246, 247, you talk about enthalpy, delta H. And again, what they do is they help you derive it in a little bit more detail. And then they give you a sample question on page 250. So my recommendation is, yes, go through page 240 at 249, 250, just for you to be able to go through this material. All right, folks, thank you very much. Sorry for the technical glitch. Have a good day. Bye-bye.